Welcome back to Learn It from a Layman. I'm Carl Christensen, joined again by Cameron and Matt, and we are together today to discuss the basics of the units of measurement. So there's a lot of different topics, a lot of different information we are going to cover in this podcast, but we're trying to keep it hopefully relevant and useful. There's a lot of measurement systems that we run into in life, a lot of different units of measure that I think that confuse the layman, such as myself, including in preparation for this podcast. But hopefully we'll be able to sort out kind of what the current state of international measurement systems is, and also what you need to know as a layman when looking at really interesting units that you might not have particular familiarity with, like ohm. All right, so let's go ahead and dive in kind of at the shallow end, because that's where you should dive. Meters, or length. Okay, so I guess to start off with, we have the International System of Units. That's or SI, the systeme. Oh, okay, Matt, can you say this in French?
No, but it's the international system, or system international.
Exactly.
With a horrible accent, but yes, that is what SI units is,
Right,
often
exactly.
referred to as metric.
Okay, well, there you go. And so for length, which is the one I think when we talk about units of measure, the first thing that jumps to mind is, okay, you're talking like meters. In the United States, we don't, of course, with like the holdovers from the old system, the English system, and we use feet, yards, which isn't according to conventions these days. But so we're going to talk about meters. So the meter has an interesting history. Meters was originally defined here a couple hundred years ago as 1/10,000,000th of the distance from the equator to the North Pole. So that's an interesting background in the history of what a meter is, and since then it's gone through some different iterations to kind of refine it. Currently, it's defined as the length of the path traveled by a light in a vacuum in 1/299 millionth of a second, almost 300 millionth of a second. So that's not particularly useful as far as, but obviously in practical terms, we're talking, an average adult male, probably in Europe and the United States, are approximately, just under 2 meters tall. And so a meter is the international standard way of measuring length. Matt, did you
Speak for yourself.
Significantly under 2 meters tall.
Okay, well, Cameron probably over 2 meters tall, right?
Yes, right. 5'17".
So, Matt, anything else about a meter that I need to?
Yeah, maybe we should kind of cage the discussion a little more in terms of what these units are and kind of the overall structure of units.
Sure, go ahead.
And what I mean by that is, within all of these units of measure, you have some fundamental units that they don't break down any further than a certain basic level. Length is a basic unit of measure. There's nothing simpler than length. Likewise, for time, the second is a very basic unit of measure. You can't break time down into anything derived. But there are other units of measure that are amalgamations or constructs that are based on those basic units. Another base unit is mass. We use kilograms for mass. If you take mass and length and time and you smash them together in different ways, you can get different derived units like force and pressure and things like that. And so we'll step through the basic units, and then we'll talk about some of those derived or secondary units and what they mean, why they're important, why you do or possibly don't care about them. On top of that, there's another, sorry, let me go to one more. There's another class You can call this coherent derived units. This is where you take one of those basic units like length and you combine it with itself in some weird way, or another type of unit. Anyway, area. Area is a coherent derived unit. It's meters squared, meters times meters, length times length. Volume is another one, length times length times length. That's an example of a coherent derived unit, just another class that we'll talk about as we jump through the different ones.
Yeah.
Sorry, you were saying?
No, I was going to say, yeah, I think that's it is useful to put that structure around it. Starting with talking about length is something I think that the layman's familiar with, but it is also very useful to understand that there's this whole very basic construct and structure to defining what a unit of measurement is, like Matt just said. So in the international system of units, like Matt said, there are these base units, and there are 7 of them. So we're going to discuss, we'll touch on a couple of them more in depth than others, and then Matt will give us a few other derived units that I think we run into frequently. And but yeah, meters being one that I think everyone's familiar with. The other 6, so there's 7 total, but the other 6 base units are the second, which Matt touched on. We'll talk a little bit about each one of these, but the kilogram, the ampere, the Kelvin, mole, and Candela. And so each of these have their own abbreviations. They each represent different quantities. And as we talk about each one of these, we're going to discuss what those quantities are and potential derived units that you'll see that might be useful to you, and some constants that you might need to be familiar with in order to understand what these units are. Now, this is a podcast I think a lot of people might gloss over in favor of touching on in calculus or something more. There's no system of units class in college that I'm aware of, but this is very fundamental to lots of your physical science classes. And understanding these units of measurement will give you a better understanding of lots of these chemistry related or physical science related or any of these hard science related subjects use these measurements obviously all the time. That's it's very foundational to being able to make any type of discovery. So let's talk briefly about the second. The second is, once again, one that the layman is familiar with. And in order to, once again, Matt said these are base units. We don't, you don't go further down the time. You could say, okay, well, what about a millisecond? Well, that is, once again, you establish a base unit, the unit of a second. And everything is derived based on that. So in the case of a second, the definition is the duration of the number of periods of radiation corresponding to the transition between the 2 hyperfine levels of the ground state of cesium-133. All fancy words essentially say it's derived. You get what the length of a second is based on a measurement of the cesium-133 atom. Matt, anything you might add to that, or something that would make that clearer?
Yeah, just well, like you were saying, the second is a base unit. Any other measurement of time is derived from the second. Millisecond is a fraction of a second. A minute is just a whole bunch of seconds. An hour, same thing. It's all derived from that base unit, the second. And the second is defined, as you were saying, essentially by the amount of time that it takes for a cesium-133 in its ground state to jiggle a whole bunch of times. Like, what is it, 9 billion times or something?
Yes, that's correct. 9 billion.
Yeah, 9 billion jiggles of a cesium-133, and that is 1 second.
Which is not particularly relevant to our general day-to-day interaction with seconds, but is how do you define what a 1 second is. I think it's important for the layman to understand once again just that 9 billion gigawatts of the cesium-133 atom sounds about as esoteric as you could get. It is important that we have some type of reproducible way of saying, okay, this is exactly what a second is, as opposed to however long it takes for your watch hand and then the gears inside of it to tick or whatever, you know.
Well, and these definitions have changed over time. The meter used to be defined as the length of a metal bar that was kept in some vault in France. And that was the meter stick. That was it. The meter was the length of this bar. And then people realized, actually, bars made out of metal decay over time. We got to figure it out to something that will never change, a more correct and scientifically based definition. And that's why the meter became the distance that light travels in vacuum in that fraction of a second. That's why time, the definition of a second, has now become 9 billion cesium-133 atomic giggles. I don't know that the International Committee recognizes the term jiggle, but you get what I mean.
But they should. No, I actually I saw this video that I think is relevant to this subject of just being able to tightly define something. I think that the layman can better understand. So here, I don't know, a number of months ago, David Spade went golfing with Tiger Woods.
This is definitely where we want to get our scientific knowledge.
I think so. No, but this is important here. And at one point, David Spade was saying something about to Tiger Woods about using a guesstimate for distance in the golf course or whatever. And he said, "Oh, you probably use guesstimates sometimes too." And it was funny that Tiger Woods just smiled and laughed, obviously implying that no, I actually don't do that. The guesstimates are not part of the best golfer in the world's vocabulary, right? They have exact measurements. They know exactly, and that's once you get in the physical sciences, saying, "Oh, we think seconds are about this." That's not going to cut it when you're in CERN and measuring, how fast a subatomic particle is traveling. You can't kind of know what a second is or a nanosecond. That these things have to be very tightly defined in order to make these precise measurements that will, help us define the rules of physics. So guesstimates are good enough for the layman, but a better understanding of and better definition of a meter, instead of just a metal bar, an actual exact distance as defined by the speed of light, by a constant. These things matter when you're doing very fine and important measurements that are going to help us define what laws are. So hopefully that Tiger Woods analogy landed, but if not, you can go watch the video and at least you'll be entertained. Okay, let's move on to kilograms. So we've got
that's
seconds.
A great idea.
Okay, seconds and meters we've discussed. Now kilograms, once again, kilograms very familiar to, I believe, once again, everyone in their day-to-day life. Probably, okay, not in the United States, and I guess that's our biggest listener base. So if you're not familiar with the kilogram, that is a measurement of mass so we use pounds to measure weight here in the United States. Kilograms far more useful elsewhere.
Oh boy, sounds like we just made a layman error right here.
Can't say.
Yeah, difference between weight and mass, I understand, but
is massively significant and frequently overlooked. Pounds and kilograms are not interchangeable.
But will you weigh yourself? Okay, well then maybe you should. But you weigh yourself in kilograms outside the United States, right?
No, that is a layman misconception. And now is as good a time to hit on this as any, but we'll come back to it in more detail later.
Can I talk about it?
Yeah, actually, go right ahead.
All right. Okay. So mass is a constant. Weight is not. Weight is based on the pull of gravity. So if you lived in Jupiter, it has a higher amount of gravity, so you would weigh more or less on the moon. So that's why you use mass because it's a constant.
Yeah, mass is defined as the amount of stuff. It's your mass.
Okay, so yeah,
The
so
amount
weight
of
is
stuff will never
weight is
change.
proportional to mass.
Yes, depending on the local gravitational forces and wells.
Right. So it's more of like a derived unit. It's a
It
combination.
absolutely is. And what it really is force. Weight by itself is not actually a recognized measure unit. It's force. Pounds are force. The metric analog to pounds is actually newtons. If I'm over there in the UK, I don't weigh myself and say, oh, I weigh, 50 kilograms. I weigh a certain number of newtons. This is why British people are so unhappy all the time. They have to talk in newtons when we can talk in pounds.
Depending on what part of the UK, they might weigh themselves in stone.
Right, and that's just all kinds of messed up.
Hey, our second biggest user base is the UK, so you need to watch out.
Poor guys. So we should be clear. We're going to focus on metric or SI units, even though in the United States we're kind of backwards about this, and I don't understand why. I mean, the units that we use most often, miles and pounds and all of that comes from a system known as the British system or imperial units. And you'd think that the United States, being one of the first to throw off the shackles of the crown, we would have been one of the first to jump away from British units. But no, for some reason, we're still stuck on that. I can't understand why. As an engineer, it drives me nuts. But anyway, yeah, we're going to focus on SI or metric units here.
Correct. Yes. I mean, in as much as it's more scientifically relevant, even though your listeners all hail from places that would probably, well, maybe not all, but a lot of our listeners would prefer us to talk about pounds, but we're not going to.
Yeah.
So
let's get back to kilograms and
yes, kilograms. Okay, so not weight. Weight is a proportional.
Weight is a force.
Yes, exactly. And
kilograms is mass.
It is an amount of mass. And
it's an amount of matter. Mass means some amount of matter.
Okay. And the kilogram, it says it's defined by setting the Planck constant h to 6.626 and whatever to 10 to the negative 34th, given the definitions of the meter and the second.
Yeah.
So
what that means is that the kilogram used to be literally defined as the mass of some wad of metal that was kept in France somewhere that was labeled this chunk of metal.
I don't think that's what they label it as.
1 kilogram. It absolutely is. It was the same as the meter bar.
Right. I actually see it. There's pictures of that.
So. And it ran into the same issues that over time, that 1 kilogram mass would shed matter through natural decay processes. And so you couldn't keep that as a lasting standard. And you had to come up with something that was more mathematically correct. And that's a little bit easier to do with length because you have the speed of light that you can measure. It's not too hard to do with time because you have your friendly cesium atom. But it is a little bit more difficult with mass. Fortunately, there is a mathematical constant known as the Planck constant that relates mass and length and time all together to one number. And when you smush those things together, you get the Planck constant. Well, because you have that relationship, if I say that my total, my Planck number is going to be whatever it says that it was, 6.626 times 10 to the negative 34th, I'm just going to say that that's what it is. Well, I already have my definition for seconds. I already have my definition for meters. That locks my definition of kilograms as well and makes it a perfect, repeatable mathematical construct that will endure forever. And so those first 3 base units are all independent and yet at the same time tied together by that Planck constant.
Planck has come up in the podcast in the past. So I lived, I believe, at the turn of the 20th century, a contemporary with Einstein, if I'm not mistaken.
And
so,
Blackbeard, yes.
Blackbeard,
Never
the
mind.
pirate.
Don't worry about it.
Oh, walk the plank. Okay.
I'm sorry.
I get it now.
It wasn't worth getting.
Okay. All right. But yes, now we've established what mass is and how mass and length and time are related given the Planck constant. So those are the first 3 units of measurement, base units of measurement. So let's talk about ampere. That is your electrical current measurement. And that is one that a layman is not familiar with. And as I so frequently do in these podcasts, represent the layman, I have almost no familiarity with ampere. Now, I think you see it occasionally. You notice it, though I think goes well over my head, at least, when you're looking at a plug and it says, 20 amps. What an amp exactly is has always kind of escaped me. I try to match numbers to numbers, but it's the flow of electricity 1 over a very large 1.602 times 10 to the negative 19th times elementary charge E per second.
Yep.
That is the definition of an ampere.
Yeah. So it's a measure of flow, except it's electrical charge flow. Think about the flow of water. And we measure the flow of water in, gallons per minute or liters per second or whatever it is. But when you're measuring electrical charge, you're not looking at kilograms or mass. You're looking at charge, and so instead of mass per second, have charge, essentially per second. And so an ampere is a little bit
flow of electrons, right?
A what?
You're basically measuring the flow of electrons.
Yeah. Yep. You're measuring the flow of charge, the flow of charges. And 1 amp is approximately 6.2 times 10 to the 18th charges per second flowing. The big thing is that's really how much electricity you have running through your wire.
So the more amps, the more dangerous it might be to interact with the electricity coming that is in your home.
Yeah, don't touch amps.
Okay.
That was terrible, but
yes.
Yeah.
Yes, exactly. Okay, let's move on. So that's electricity.
So here's a good real world example. So when you're charging your phone, you'll see different amperage, like 2.3 or something like that. The lower amps charge your phone slower because it has a slower flow of electricity versus your higher amperage. But a really high amperage will burn your phone out.
Yeah, it totally will. If you put too much flow through it's just like water. If you put too much water through too narrow of a channel, it's going to flood and ruin everything. If you put too much charge through a insufficiently sturdy conductor, it's going to burn, melt, explode, those types of things.
All bad words.
All bad words. Very good.
Things you certainly don't want to happen to your phone. So don't do that.
Or your house or anything else.
Exactly. That's good. Thanks, Cameron. Okay. Kelvin. So this is obviously the measurement of temperature, specifically thermodynamic temperature. We have a podcast about the basics of thermodynamics where we talk about Kelvin, but in the context of this podcast, we're just talking about obviously measurement of movement, molecular movement. So as the Kelvin is defined by setting the fixed numerical value of the Boltzmann constant K to 1.38 times 10 to the negative 23rd joules, given the definition of the kilogram, the meter, and the second. So once again, it's another constant that that involves some of these other base units in order to give us an exact measurement of thermodynamic temperature. Now, the interesting thing about Kelvin, which once again we've touched on in the past, is at 0 degrees Kelvin, so this is measured in degrees, you have absolute zero. That means no movement, no molecular movement. It's unattainable. I can't get to absolute zero. And what else am I missing, Matt?
No, that's pretty much it. Kelvin is temperature, and just like the Planck's constant and mass with kilograms, you have the Boltzmann constant relating some of those other base units in such a way that we can mathematically define what temperature is, what Kelvin is.
Yeah, so not that it's going to necessarily stick, but if you want to relate Kelvin to the scales that we use more frequently or more familiar with, so Celsius for most of the world and Fahrenheit for the United States, because we like to do things differently. In water on the Kelvin scale freezes at 273.15 Kelvin.
Yes.
And it boils at 373.15 Kelvin. So given that we know where and when water boils according to the other scales, obviously in Celsius, we're talking freezing at 0 and boiling at 100, and in Fahrenheit, randomly 32 for freezing and 212 for boiling. So it gives you kind of the idea that Kelvin is a very different scale, obviously measuring something more accurately and specifically thermodynamic movement. Once again, I did want to do a quick aside because, like I said, most of the world's familiar more with the Celsius scale than Kelvin. Just his interesting historical fact. So his Celsius was originally, so it's named after a Swedish astronomer, Anders Celsius, and his scale actually was the opposite. He had water boiling at 0 and freezing at 100, but there was other scientists that had the scale developed about the same time, and it had to flip, and that obviously made a little bit more sense to most people, and so that's what stuck. It is named after Celsius, however, Anders Celsius, Swede, and familiar with it being a centigrade scale, meaning 100 grades. So from 0 to 100, obviously, and measuring water freezing and boiling. And so that's how we get the scale that we use most frequently, the one that most of us are more familiar with when talking about, say, the weather outside. We don't generally give that in Kelvin.
Well, yeah, I mean, the conversion between Celsius and Kelvin share the same scale in terms of 1 degree Kelvin and 1 degree Celsius represent the same amount of relative thermal change. It's just that the scale starts at a different place. Kelvin starts with 0 at absolute 0, and Celsius starts with 0 at 273.15 Kelvin, or the freezing point of water.
So, I mean, I think we should kind of talk about when Carl was giving the definition of Kelvin, he mentioned joule, which is a term of energy. And so when we're talking about the thermodynamics, that's why we're talking 0 Kelvin, which means there's no energy produced, so no movement. So that's kind of based on kind of goes back to what you were saying.
Yeah. Like I said, all of these things are related, and so it's hard to, we're talking about base units. You think, oh, each one stands alone, but stands alone in that they all have important places in defining each other. Therefore, it's like a prime number, but yeah, they certainly are interrelated. And okay, let's move on now. We are on, let's see, where are we? We are on moles. So that is the measurement of the amount of a substance. And so when we're talking about measurement of the amount of, when we think mole, you think about your chemistry class, you think about measuring atoms. So amount of substance is exactly 6.022 times 10 to the 23rd elementary entities. This number is a fixed numerical value of the Avogadro constant when expressed in the unit mole to the negative first power. Okay, so moles, we're measuring the amount of the substance, we're measuring atoms, and once again, familiarity with this, I think, is mostly in chemistry class. Anything to add, Matt or Cameron?
Yeah, the really handy thing with the mole is that this is the amount of atoms that you need to collect in order for your sample of some element to have close to its atomic number to get the atomic number of the element as mass in grams. Okay, what do I mean by that? That's weird. Well, carbon 12. Carbon is right there on the periodic table. That's the thing. And if you have Avogadro's number of carbon atoms, 6.02 times 10 to the 23rd, if you have 1 mole of carbon atoms, then you have 12 grams of carbon. And likewise with hydrogen, if you have 1 mole of hydrogen atoms, you'll have roughly 1 gram of hydrogen.
Okay.
It is not precise for all elements, but it gets you generally pretty close. And you can find tables in your chemistry textbook that show you exactly how much mass you get for 1 mole of each element. And in general, it's pretty close to the element's atomic number.
Right. Okay. Let's move on to the last base unit of measure, and that is the Candela. I think I'm pronouncing that correctly. Once again, zero day-to-day familiarity with this one. We're measuring luminous intensity. So I'm measuring, it says it is in a luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 5.4 to 10 to the 14th hertz and has a radiant intensity in that direction of 683rd watt per steradian. Thank you. Layman reading scientific definitions, going well. But this is measuring, obviously, it says luminous intensity. So, Matt, how does that relate to what we talked about? We had a podcast a long time ago about frequencies and the electromagnetic spectrum. Is this related to that?
Yeah, it is. So the definition has you assume a certain wavelength or frequency of light. And what was it? It was 5.4 times 10 to the 14 hertz.
Right.
So, that wavelength of light, if you take whatever color that is, and you emit it from a source that has a certain amount of brightness, that's the radiant intensity. If you have that shade of light and you emit with a certain brightness of source, you'll get a certain amount of light at another point. And that is your luminous intensity. And that is what the candela is. It's the light that you get out of a given source. 1 candela being defined as the light that you get from assuming that you're emitting whatever shade that is, that frequency, and that you are emitting with a certain base brightness, if that makes any sense. So a certain shade, a certain power, if you will, put that together and you have the very basic foundation of the candela.
Okay, and this might be a good time to review. So once again, I think this came up in our podcast from a year or two ago about what hertz is. Also another unit, and it comes up in the definition here. So hertz relates to measuring waves, right?
Hertz is cycles per second.
Right.
And it relates directly to time. It's a derived unit from time and time alone. It is actually 1 over time. So if you have 1 second, you can think of hertz as 1 secondth. No, you can't. That's terrible.
Okay.
But yeah, it literally is expressed as 1 over s
Okay.
for seconds, or 1 over t for time.
Right. And if anyone else, sorry.
I'm sorry, hertz really is 1 over s for second. That's what hertz is, cycles or activities per second. And that's why we call it frequency. It's how frequently something happens. It happens a certain amount of times every second.
And if you want a more in-depth discussion of the measurement of time, because I know we talked about that here half an hour ago briefly about the seconds and how how we get the duration of a second by the cesium atom. We didn't discuss that specifically, but we do have a podcast about the measurement of time. So we're bringing a lot of our podcasts here together in order to establish this unit of measurement framework for all of these different fields. But let's talk about a couple other units of measure. So we've talked about these 7 base units, and then Matt discussed derived units and how you can get put these together and these base units together in order to get a derived unit. But there are a few that we interact with frequently and or are used even to define some of these base units. So let's talk a little bit about. So we talked about newtons. Matt, what is exactly 1 Newton is amount of force, right?
Yeah, let's talk about force and then pressure if we could.
Yeah.
So force and weight, they're often used interchangeably and they're often confused together, and at some level they are interchangeable.
Earlier this podcast.
Well, yes, there we were confusing force and mass.
Right.
But I'm talking force and weight, and well, it is just that. It is the mass of something multiplied by an acceleration. And here on planet Earth, we've talked about in other podcasts how there is a constant acceleration down towards the center of the Earth that's brought on by gravity. And at sea level, that acceleration is 9.81 meters per second squared. Well, if you take that and you multiply that by your mass, you get your weight. You get the amount of force that that gravity exerts on you.
Okay.
And that is measured in newtons. And again, the unit for newtons in SI units is it is kilograms times meters over time squared, or over second squared. So mass times length divided by time squared. That's how you get force or newtons. The analog for force in the ye old timey British units is pounds.
Right.
And we don't speak of pounds.
Except that we do almost all the time in the United States.
Yeah, I know. All right, so let's say that you have that force and you want to use that force to determine how much force you're going to apply to a thing. Well, that's kind of where pressure comes into play. Pressure is measured in force on a given area. Now, we kind of hinted at this, but area has its own measurement, and that's length times length, meters times meters, or meters squared. And so pressure is just force on an area, so it becomes newtons per square meter. Now, what you had before, if you remember, because you all wrote this down, newtons are mass times length over time squared. Well, if you take mass times length over time squared and you divide that by length squared, one length cancels out with the other length, and you're left with a single remaining length in the denominator, you get kilograms over length times time squared. Kilograms divided by meters, divided by seconds, divided by more seconds.
Okay. And that's
newtons per meter squared. That's pressure. And
right.
and I'm sorry, I haven't even said the name of this thing.
That's
the unit is the Pascal. The
right.
shorthand notation is capital P lowercase a.
And where is that used, Matt?
In pressure. Now, again, ye old-timey analog is pounds per square inch, PSI.
Right. And that's what the layman is familiar with, right?
Right. Well, if the layman is an American.
Right.
But yeah, I mean, you use this for all kinds of things when you're building submarines, when you're pumping up your CO2 gun, whatever, air compressors, all of these things. Anytime you're looking at pressure, you're looking at PSI, pounds per square inch. And remember, pounds is just force and square inch is an area. Or if you're getting with the rest of the modern world, instead of using pounds per square inch, you use newtons per square meter, and you have pascals. So that is pressure.
Really quick aside before we move on, because I think we're going to hit one or two more before the end of the podcast here. But I did want to invite anyone that's listening to this podcast. So I always try to talk about a new area of the world that's either tuned into our podcast or something along those lines. So our last podcast being an interview and a discussion of Taiwan with Brent Christensen, who was the director of the former director of the American Institute in Taiwan. He obviously has piqued a little bit of interest in Taiwan, so our Taiwanese audience has grown significantly. So welcome to anyone listening either in Taiwan or the Southeast Asian area. So we've got obviously a number of people listening from there. And if you have any interest in Taiwan, I recommend our last podcast, a lot of information from a very knowledgeable guest. So that is our aside to our listeners. But let's move back. Okay, so Matt just described pressure. What about joules? We talked about joules in relation to they help define a few of the, or at least one of the base units of measurement. What is a joule?
A joule is a complicated nightmare of a unit because it immediately leads into all of these other units having to do with heat, work, power, charge, and all these other things. Recommend that you know, some of our viewers maybe go back to the basics of thermodynamics, I believe, where we talk about some of that. But in short, joule is energy or heat. It is, well, it's just that. It is a derived unit, and it is mass times area over time squared. So mass times meters squared over, mass times length squared over time squared. In SI units, 1 joule is 1 kilogram times 1 meter times 1 meter divided by 1 second squared.
Okay, that was complicated.
I know it is. Think of it as just energy. And then if that doesn't work, think of it as power. And then punch yourself, because that is totally different. It's a different unit. Power and energy are not the same. And power is measured by our next unit, the watt. And a watt is, and power are defined as energy per second. 1 watt is 1 joule per second. I talked about a very basic analogy with a light bulb. If you light up a light bulb, it consumes energy, and it consumes energy at a certain rate. Every second, a 60-watt light bulb consumes 60 joules of energy, 60 chunks of energy. And it will consume 60 chunks of energy every second until it burns out and dies. And that is That's the relationship. You have a certain amount of energy that's being chewed up in a certain amount of time, and that gives you your power. Your power is your energy in a certain amount of time. Watts specifically being 1 joule of energy per second is 1 watt. Any questions on power and
I
energy?
think it is important to relate this to the gigawatts in Back to the Future.
Yep, 1.21 gigawatts. I don't know why they pronounce it gigawatts. Maybe that's right, but if it is, I refuse to believe in science anymore. That's 1.21 billion watts, which is the same as 1.21 billion joules of energy, little energy chunks, consumed in a single second.
And when you deal with time travel like they do in that movie, seconds really come into play as well.
Yeah, now here's the thing that's interesting. When you think about it, to power that flux capacitor, what did he actually need? It said he needed 1.21 gigawatts, but is that correct? Because watts is flow. It's an amount per second. I could give you 1.21 gigawatts, but if I give it to you for 1 billionth of a second, how much energy have I actually given you? I've only given you 1.2 joules. Is that enough to power your flux capacitor? Absolutely not. So that movie, shockingly enough, may have contained a scientific inaccuracy.
I find that incredibly hard to believe.
I know. But Dr. Brown did not need 1.21 gigawatts to power his flux capacitor. He needed a certain amount of joules to power it, and he needed to get that amount of power at a certain rate. So his statement that he needed 1.21 gigawatts is incomplete. At minimum, he should have said, I need 1.21 gigawatts for a certain amount of time. Yeah, I know.
In the remake, I'm sure that they'll get that correct.
I don't know if I can continue to listen to this podcast.
I know. We probably just lost our audience from 1985, but that's okay.
Okay. And
all right, let's talk about a few more before we close
let's
up.
say 1 or 2 more, and then we'll wrap up.
Yeah. Those 3 that we just talked about, the Newton, the Pascal, the joule, and the watt, those 4 that we just talked about, that's what I said. Those are derived units. They all relate back to those 7 basic units. There are still more, the coherent derived ones that I mentioned, and I just want to hit a few of them. I already talked about area simply being length times length, and volume being length cubed, length times length times length. A couple others that are important. I've mentioned acceleration before. That's meters per second per second. And acceleration relates to, well, it's tied to motion. And when we're talking motion, we're talking velocity as well. Velocity or speed is simply distance over time, length over time, meters over seconds, meters per second. Alternatively, if you are stuck in British peasantdom, it's miles per hour. It's a distance per time. Acceleration is the change in velocity in a specific time. So in order to capture that, I have to have velocity as part of my unit. That's my meters per second. And the change in that over a certain time. So meters per second per second. That's what acceleration is. The change in your meters per second every second. Meters per second squared. And I mean, we could go on and on in some of these other units, but those were kind of some of the basic ones. The last and final one that I wanted to hit was density. And that is just how much stuff, how much mass you have in a specific volume. So mass, kilograms, volume, that's going to be length times length times length. or meters cubed. How much mass in how much volume? Mass per volume, that's kilograms per cubic meter, kilograms per meter cubed. So that's your measurement for density. And there's a number of others, and feel free to look up some of these more or less esoteric ones, flux, luminance, all of these other things,
Tesla,
conductivity and so forth. Teslas, that's a unit. But that I think is kind of a good introduction to some of the more common units of measure that you'll run into in basic physics and your introduction to some of the different sciences.
Yeah, I think it's really useful, once again, to have this framework and an understanding of why this would matter, having an exact understanding of what these different units mean and how they are interrelated. Obviously, it's going to be, like Matt said, very useful in these hard sciences. But I think this is a very basic human thing. We can measure. I think you come out of the womb measuring different things. As a kid, you're measuring how far you can run, how fast, and so it's a pretty basic instinct to measure. And as we progress in science, our measurements are more and more exact, and that helps us make these improvements in our understanding of the world and the laws of science. So once again, I hope this was really informative. I hope this was relevant. And I will, any last words, Matt or Cameron and Tim, who's joined us?
I hope not. I intend to be on this podcast in the future. Thank you.
Final words about units of measurement and or Back to the Future.
Remember, kids, winners don't do cesium.
9 billion jiggles.
I don't think we can end on a better note than that.
You would be so incorrect. Have you listened to this podcast before?
Where's that Rammstein music?
Okay, Cameron.
Don't get confused with the mole that lives in the ground and the amount of atoms that make up.
Yeah,
but don't. A T-shirt. You have a picture of a mole and then 6.02 times 10 to the 23rd.
There we go. Another merch that our podcast is going to create. Okay, wonderful way to end the podcast. Thank you, Cameron. Yes.
All right.
Tim?
I'll just say that, speaking of measurement, my time spent with you guys is timeless.
Oh my gosh. Cut that. All right. Well, once again, thank you. Hope you understand better units of measurement and join us again in the future for a discussion of we're going to be talking about all these other podcasts that we've teased. We will deliver on. We delivered on this one. We're going to deliver on the other ones. Tell your friends, rate us on follow us on Spotify, all those different things. And we will see you back for our next podcast.